In this video, we're going to talk about arc length, the definition of it, how to find it using a formula, and maybe how to use it to find other variables like radius or central angle. First of all, arc length is a fraction of the circumference around a circle. So circumference is all the way around the circle. What's the distance? Kind of like the perimeter of a rectangle, but in this case it's not a polygon, it's a circle. Arc length is taking 2 points and asking how far is it along the curve here from this point to this point. Notice how I'm not asking for the straight line distance across a circle. It's around the arc here. Okay. So what you're going to do is you're going to find the entire circumference and then find what fraction of the entire circle this arc is, and you multiply them together, much like the area of the sector formula. So the formula, we're going to use the letter capital S for arc length because most of the letters are taken for other things. At the end, you'll notice I'm going to put the circumference formula, 2 pi r, because you need to find the entire circumference first. The entire circumference for that part. And then you determine how much of the 360-degree circle is this arc taking up. You know, is it a really big angle like 270 degrees, or is it a small angle like 10 degrees? So it'll change how much of the arc it actually is. So we have 3 variables here: arc length, S, theta, central angle, R, radius. So I can give you 2 of the 3 variables and ask you to solve for the third. So if I ask for arc length, you need to have central angle, radius. If I ask for theta, you'll need arc length and radius. And finally, if I ask for radius, you'll need arc length and theta. Look at a couple examples. The directions say find the length of each arc, round your answer to the nearest tenth. Number 12 gives you a couple bits of information here. We have a formula I'm going to copy down real quick. They're asking for arc length, so we don't know what S is. That means I have to have central angle and R. Central angle, 45 degrees, is given. Check that off our list. Radius, 14 meters, also given. We can check that off our list. So we're going to find arc length. We need to plug in those 2 numbers here and calculate. So 45 degrees goes in for theta. 14 meters goes in for R. And since we're going to approximate this, you can type this in all at once. 45 divided by 360 times 2 pi times 14. I'll show you how I type that in. Calculator right here. So 45 divided by 360 times 2 pi times 14. And the arc length is approximately 10.995. So nearest tenth would be here. The 9 makes this go up to 11.0. And the units are meters. Now I know the actual arc appears in 2 dimensions, but it is still a length. It's a 1-dimensional measurement. Okay, so imagine taking this curved piece and laying it out flat. It's still a 1-dimensional length. So we used theta and R to find arc length. Let's do another example where they give us different initial information and trying to solve for something else besides arc length. So look at number 16. It says find the central angle if the diameter is 12 meters and the arc length is 12.6 meters. So the diameter is 12 meters and the arc length is 12.6 meters. So we're going to rewrite the equation. We're going to mark what we have and what we don't have. So arc length we have. Check that off our list. Theta is the central angle we don't have. It's the first part of the sentence. That's our question mark. Radius. We don't have it right now, but we do have the diameter. And taking the diameter and cutting it in half, we will get 6 meters. So now we have it. So plug in those numbers. 12.6. Theta we don't know. Times 2 pi times 6. And since we're solving for theta, we have to get rid of everything else that isn't theta on this side. Since it's all multiplication or division, we're going to multiply both sides by a reciprocal, one reciprocal fraction. Write an empty fraction so I don't forget to copy it on both sides. So in creating this reciprocal fraction on each side, we need to take what's initially in the denominator in this part of the equation and put it in the numerator. Or if it's in the numerator, take it and put it down to the denominator. So what's on top goes on bottom, what's on bottom goes on top. So start with 360 currently in the denominator. That goes to the top so that it cancels out here. 2 pi 6. All of that is in the numerator of a fraction. Even though you can't see the 1, it's there. So put all of that down below. So all of it cancels out. And you're left with just theta on this side. Now repeat this fraction over here. 360 over 2 pi 6. And we're going to type this in all at once and approximate it. So it's going to be in degrees. I'm going to show you how to type it in right now. We're typing in this piece right here, 360. So it's going to be 360 divided by, I'm going to use a set of parentheses to help make sure that the calculator knows that all this stuff's in the denominator, 2 pi times 6. And then times that by 12.6. Notice how I closed the set of parentheses because this 6 is the last number in the denominator. 12.6 is not in the denominator. So you put it in the parentheses, you're telling the calculator the wrong thing. Press enter. 120.32. Let's run to the nearest tenth. 0.32. It's going to stay the same. We're going to truncate it down. So 120.3 degrees. So theta is approximately 120.3 degrees. So, recap, we have the central angle that's being asked to find. They have to give us R and theta, or R and S to do that because there are 3 variables. We need to give you 2 of them to solve for the third. All right. So the definition of arc length again is just a piece of the circumference. So how far between 2 points along the curve is it? So it could be a smaller or less than half piece like this. It could go further than that. It could go more than half, really close to all the way around, depending on the situation. The larger the arc, the bigger the angle will be in the middle, the central angle. And it shouldn't be that difficult to remember. This piece here is the old circumference formula of the entire circle. All I'm adding in front is the fraction of the circle of which it's going to take up. And we measure that by the angle out of 360 degrees, the total all the way around the circle.